Hello everyone, welcome to today's session on cache memory mapping. As I told you in earlier lecture, cache is a memory that is the fastest memory one can have. Now, let us understand that why cache mapping matters. But before that, we need to understand that how the cache is used, right? So when the CPU needs to access a memory, you are having a CPU, right? And then you have a main memory and you have cache memory. So when your CPU needs to access a memory, first of all, it goes to the cache memory, right? So the cache is examined first, and if the word is found here, it is available in the cache memory, it is read from that memory and CPU will get the access of that particular data. But if it is not available in cache memory, then next is what? So next is the main memory is then accessed by the CPU and it will get the data, it will read the word from the main memory. At the same time, the block of word that is like just exist, right, by the CPU, that is transferred into the main memory, right? So this is the entire process, how the cache memory is working, how CPU access the cache memory and the main memory, right? So first thing is cache memory stores the frequently used blocks from main memory for rapid CPU access, because we need efficiency of CPU, right? We need efficiency. So for that efficiency, cache memory is the fastest memory and the transfer rate of cache memory is very high, right? So the frequently accessed data is stored in cache memory, right? And that is then transferred to the CPU, right? The second thing is for that performance boosting, as I told you that if it is available into the cache memory, then CPU will take it from here, and if it is not available, then it will bring from main memory, right? So there comes the word hit ratio, right? You might be aware of the hit ratio. Now what is a hit ratio? So hit ratio is like when CPU refers to the main memory, right? And when CPU refers to a particular word, right, and first is refers to the cache, if it is available in a cache, then it produce a hit, right? If that particular data is available into the cache, then it called hit, right? If it is not found, if that particular word is not found in cache and it is in the main memory, so it will count it as a miss, right? So you understand that what is hit and what is miss, right? And the ratio of the number of hits divided by the total CPU reference, right? Hit ratio, that is equal to I'll write it over here, that hit ratio that is equal to number of hits divided by total CPU references. So suppose CPU made 10 references, right, and out of that 5 is a hit, right? So your hit ratio is 5 divided by 10, right? And based on that, the performance of the cache is examined, right? So for boosting the performance, right, so we need to have a high heat ratio, right, that means reduces the cache misses, right. So it will result in the high heat ratio and it will improve the system's efficiency, or you can say performance, right. So this mapping is what? So mapping determines where a main memory block resides within the cache, right. So mapping in a general language, we can understand that what is mapping. So mapping is a transformation of data from main memory to cache memory. I told you that when the data is not available into the cache memory, it will brought from the main memory, right. So that method is called mapping, right. So basically we are having three types of mapping, right. Associative mapping, direct mapping, and set associative mapping. So let us understand those one by one. So we'll start with first direct mapping technique, right. So you can see the diagram, right. Diagram is available here, right. So direct mapping technique means what? It goes one to one, right, one to one correspondence, right. So each main memory block that is assigned to a specific cache line, right. This is like cache memory available over here, right. This is your main memory available over here, right. Now in main memory you are having this data, right. This datas are in octal form, right. Octal form, that means this data, it's 12-bit data, right. So in octal form it is like 4 numbers, right. And memory address, so that address is 15-bit address, right. So that is in the octal form, right. So this data is available over here, right. Now this is cache memory. In your cache memory, your address, like this data is divided into tag, right. So this address 00, this is 00000, that is divided into two parts, right. Tag and cache line index, right. So this two, right, that is your tag, right, and the remaining 3 is your index, right. So this 2 is your tag and this 3 is your index, right. So when this data, I want to store this data 1220, its memory address is 00000, so it is divided. Now this last 3000, it would be considered as an index, so that is here available, index 000. Then we'll store the tag in a memory, right. So in a cache memory it is divided into two parts, tag and data, right. So in a tag part we store the 00 over here, in a data part we store the data, right. Similar way you can see here that here we have a 02777, right. So the data is 6710, right. So it is divided into two parts, 02 and 777, where 02 is your tag and 777 is your address. So at the location 777, this data 6710 is stored along with the tag 02, right. So when CPU access the data, so first what it will do, it will divide the address into the two part, right. Suppose I am searching for a data available at the address 00777, right. So it will divide it like 00 and 777, right. So first what it will do, it will search for the 777 location, right, and then it will match the tag available at that address with the currently available tag, right? So here it's a 000 and here it's a 02. The both are not matching, that means it's a miss, right? And if it is a miss, that means then it will access the main memory, and that data is brought from that main memory, and CPU will access that data along with the same thing. This data, this 02 at this location 777 is replaced by the data available over here, right? Now instead of this, suppose CPU is asking for the data available at the location 02777. So it will divide it like 02 and 777. Again the same, it will search for 777 and it will match the tag here 02, here also 02. Now it's a match, right? So it's a match, that means that data is available over here, and that CPU will directly access the data from the cache. So it's a hit, right? So this is the technique of direct mapping, right? So I hope you understood this direct mapping, right? Now what is the advantage of it? So it offers a simple hardware, very basic hardware, and it will give you a fast access. But here one issue is that the number of misses, the chances are very high to have a miss, right? So conflict misses, and if frequently used block map to the same line, so we have a very good chances to have more misses than the hit, right? So now next we move towards the next mapping technique, right? So the next mapping technique is associative mapping, right? Now this associative mapping is like you might be knowing about the associative memory, right? It access the associative memory, right? So associative memory, that is like fastest and most flexible cache organization we have right here. So it uses, here I have written content addressable memory. Content addressable memory, that is same, right? The other name for the associative memory is content addressable memory. That means where the address and the content both are stored as a memory word. This is your memory, right? So here we use SCAM as our cache. So when we use SCAM as a cache, that means here we have stored address also and data also as a part of our memory, right? So that means anywhere here the address, right? I have not mentioned the addresses, but anywhere in the memory I can store the data, right? There is no restriction. Previously it was like that we are storing the data at the address, we divided the address into two part, tag and the index. So that index, at the same address we are storing the data, right? But here we can store it in any available cache line, anywhere I can store it, right? So it offers high flexibility, right? And here is fewer conflict of misses, right? And better hit rate, because we can directly store it. Now how it works? So suppose I am storing the data available. First we tell this about the how we can store. So that, like, suppose I am having 01000, this is my address, 15-bit address. Again I'm telling, this is in the octal form, right? So this is a 15-bit address. At this location I am having a data that is a 3450, and if I want to store the data, so anywhere into the memory I can store it. So first I'll store the address, that is 01000, and then the data, that is 3450. I want to add one more data, let us say like 11111. This is the location, and I want to store the data, that is 5000. 5000 is my data, and this is the location. So I can store it over here, like this is like 11111, that is the address, and 5000, that's a data. I can store it over here, right? So that is the storing process. And how CPU access those data? So when CPU requires one data na, that address is like CPU address is given to the argument register. We have AR argument register, right? So this argument register will store that address, and with the mechanism we search that address here. With this address, suppose I am asking for a data available at 111 5 times 1, right? So argument register will hold that data 11111. It will be matched by the each line. Here it's not a match, not a match, not a match, and whoa, here it's a match, right? So it will give you the result, the data available here to the CPU, right? So that is a very basic thing, right? And this is like most flexible cache organization, that is a associative mapping, right? Now we move ahead with the last one, that is the set associative mapping, right? Set as its name suggests, right? It's a set associative mapping, right? So it's a combination of both. It's having the simplicity of direct mapping and the flexibilities of associative mapping, right? So both we are having here. So here the cache memory is divided into the set. Here as you can see, it's a two set, 1 and 2 sets we are having, right? So the cache is divided into multiple sets, number of sets, as many sets I want, right? So and it have a smaller number of cache line. That means this memory are smaller, right? Smaller number of cache line we are having, right? So a cache of set size k, if we are having a k size, here we have a 2 size, right? So it can store the k memory block per set, right? Reducing the chance of collision. So here the minimum chances of collision here, right? And it's like a flexible placement within the set, right? So suppose we have already seen in the direct mapping the same way it is storing, right? So suppose we want to store the data available. Suppose I'm having this, right? And this is my location. Suppose let us say 0 0 0 0 0, right? And here I am having a data that is 5000, right? And I am having another one that is like 0 1 0 0 0, right? And that is having 3 4 5 0. And then I have some another data at location that is 0 2 0 0 0, and that is having 5 6 7 0. So suppose the first I want to store this, right? So that is again the same thing. It is divided into two parts, right? First is a tag and another one is index, right? So at the 0 0 0 index, as you can see over here, 0 0 0 index, we have a tag 0 1. So this is 0 1. At that location I have stored this 3 4 5 0, right? At the same time, if I want to store one more data in a direct mapping, if I want to store the data, then what would happen, that this can be replaced with the another one, because that at that place in a direct mapping we don't have a number of sets, right? We are having only one memory, we don't have a sets, right? Here we have a sets. So if we use a direct mapping and if I want to store this data, then this data would be replaced, right? This data would be replaced. But I'm using this set associative mapping. That means we have another set vacant. So at that location we can store the like this is like 0 2 and 0 0 0. So same 0 0 location with the tag 0 2 I can store the data 5670, right? Now the same thing if I want to store for this 0 0 0 0 0. Now here I am having only two sets, right? So if I am having two sets and both the sets are like having full, the data is already there, if it is not vacant, then it would be replaced by the 0 0 0 0 0 using the LRU algorithm. The number of replacement policies are available, right? So using that it would be replaced. Suppose if I have one more set, right? Suppose if I have one more set, right? So here the same way, if this set is available, if it is not available, that at the end time I cannot generate one, right? But if that set is already available, so for this I can store the data like 0 0, and here I can store 5000, right? So there are very minimum chances, right, of miss here maximum, like if a CPU refers to a particular location, suppose it is searching for a data available at 02000, right? So it will go to the index 000, it will match this tag 01, not matched, then it will go to 02, yes it's a match, then it will return this data to the CPU, right? So the main advantage of set associative mapping, that it can store two or more words from the memory under the same index, right? Here we are having the same index 000, here I have stored 1 2 and 3 data, right? So that is a very beneficial thing, right? And here this is identified with the tag, right? We have a tag to identify each data. So with the same index we have a different data, so it helps us to differentiate between that, right? So this is very simple set associative mapping, right? So I hope you understood this, right? So we learned in this lecture the mapping techniques, 3 mapping techniques: associative mapping, set associative mapping, and direct mapping, where associative mapping use associative memory, or you can say content addressable memory, so where we can store both data and address inside the memory. And direct mapping, we divide the address into two parts: tag and index, right? So at that particular index, along with the tag, we store the data. And then we have a set associative mapping, that's a combination of associative and direct mapping. Here we divide the memory into the sets, so at a same index we can store multiple data with different tags, right? So I hope you understood this, right? So this is about mapping. If you have any doubt, you can ask, right? Thank you very much. Thank you for watching this video.